We got a double slit experiment. We got a lot of light waves coming in at 660 nanometers, which, by the way, 660 would be, what, close to greenish? Roy G. Biv. Starts at 5 to 8? I don't know. It'd be close to green. Watch, it tells us what the color is. They have 1.8. They got a distance of separation of 4.4 between the slits. The light waves from the two slits are coherent. In order for it to be coherent, the definition of coherent means that they will have a constant phase difference. That does not mean that they are the exact same wave. It does mean that they would have to have the same frequency and same wavelength. They could either be out of phase and continue to be out of phase, or they could be in phase and continue to be in phase. They can't jump in and out. They're going to be whatever difference they are, they stay that way. That is what it means to be coherent. It is not meaning that they are in superposition in any way, like it's just a constant, whatever superposition it is. All right. The differences in their path lengths in nanometers from the slits. For the two light waves superpositioning at R, calculate the difference in their path lengths. I got to read. So we got to look here. Superpositioning at R. Notice how R is a dark fringe. If it is a dark fringe, that means that it is destructive superposition. If it is destructive superposition, they're going to be a half a wavelength apart between this distance here coming all the way to R and the other slit going to R. They are going to be a half a wavelength apart. So because they're two different light sources are happening and they are destructively interfering, they're a half wavelength apart. If they tell us the actual wavelength was 660 nanometers, we just need to know that it's going to be half of that. So 660 divided by 2, 330. It's only a one-pointer, so that makes sense that it didn't involve a lot of work. If it were a 2 or 3-pointer, you probably would have to find the wavelength and then divide by 2. What is their phase difference? Their phase difference is in degrees. They're a half a wavelength. A half a wavelength would be a phase difference of 180 degrees. A full wavelength would be 360 degrees. Okay? Interestingly enough, oh, thank goodness. The answer key said 540, but then it said also acceptable to write 180. I was like, what? All right. Calculate the distance from O to Q. It is a 3-pointer. We need to find the distance from O to Q. I need to look at the problem. We are looking from O to Q. O to Q is from the central bright spot to the next brightest fringe. Our formula is D, I think I called it X over L. I might have said Y max over L is equal to M lambda. We are one bright spot away from the middle. Therefore, M is equal to 1. We got 660 nanometers, so that's 10 to the negative 9th. We have a distance of path length, not a distance path, like the L, how far away it is 1.8. We're solving for X, and we have 0.44 millimeters, so we would also have to multiply by 10 to the negative 3rd. And technically that means the same thing with the 10 to the negative 3rd there. I just forgot to write it when I did it. If you just solve for X by multiplying by 1.8 and dividing by the 0.44 times 10 to the negative 3rd with your fraction button, you'll get your answer right away, which is 2.7 times 10 to the negative 3rd meters. Okay? Next question. The intensity of the light incident on the double slit is increased without changing the frequency. So if we didn't change the frequency, we did not change the wavelength. Describe the appearance of the fringes after this changes in a different form, similar to the appearance before it changes. So what happened with that? 3 points, so they're expecting a lot of answers. Okay? If we look at our formula, which was d y max, or y over L, is equal to m lambda. We did not change a thing on that formula, which means that all of the bright and dark fringes are going to be in the same spot. So all bright and dark fringes will be in the same location as before. But if we increase the intensity, then it will make things brighter. That's what intensity is the brightness. So even though they're in the same spot, the brightness of the pattern will increase. And due to the brightness of the pattern increasing, in this case, it's a gradient pattern, so you might notice, the gradient a little bit more. It might be easier to see because it will actually be visible to the naked eye a little bit better. Actual answer, I'm going to show you it because they wrote a lot. All right. After the intensity of light increases, the bright fringes will appear brighter. There will be no change in dark fringes. The fringe separation will also be unchanged. I probably should have said, if it's a dark spot, it can't get any darker, so the intensity won't affect that. So that's the part I missed for the third point. So the dark spots will still be dark, but the bright spots will look brighter. All right. The wavelength of 660 is now replaced with a blue light from the laser. Okay, now we got to think. State and explain the change, if any, that must be made to the separation of the slits so that the fringes are in the same place as they were before with the 660 nanometers. So this one involves a lot of thought. Okay? So blue has a wavelength of, I think, around 550 or 500 nanometers. I think we said like 8 to 5 or something like that when we were talking about Roy G. Biv. Red has like 800, and then blue has near 500 or 550, which is a shorter wavelength than 660. Okay? So because blue has a shorter wavelength, if we look at the formula, we want the Y max to be the same. Y max is on the same value as lambda, which means that Y max is proportional to the wavelength. If we know that, that means that if the blue wavelength goes down, the Y max will also go down. Okay? So the fringes would get closer together. Two-pointer, so we might not need that. In order to counteract the closer together part, how would we need to affect how far away the screen is going to be? Well, the screen is inversely proportional to lambda. So in order, if Y max is going down, we would need to also decrease or increase the L. How would we get it to spread out further? You could actually think in geometry. If they're spread out very little and your screen is currently here, if you move the screen further back, notice how the fringes go further apart. So we would move the L, or the screen, further back to have the same fringe separation pattern. And I'll also look at the answer key for that so you guys see how close we got. Okay. Blue light is shorter than 660 nanometers. When the fringe separation remains constant, the wavelength is proportional to the slit separation. Therefore, the slits of the two must be decreased. Did I read it wrong? I did read it wrong. I explained it in terms of where should the screen be, but what should happen to the slit separation was the actual question. The slit separation would need to counteract that. If the Y max go down, then the slit separation should go down to counteract it. I did Y max and the length away from the screen. Let's read that. I'm sad. I got something wrong. But that is the end of this video. Take 2.